Welcome to Visual Algebra Lecture 3.4, Normalizers and Normal Subgroups. In the last lecture, we learned about cosets, and we saw how every subgroup has left cosets and right cosets, and both of these partition the group, though potentially in different ways. The normalizer is the set of left cosets that are also right cosets. If every left coset is a right coset, then we say that the subgroup is normal. We also introduce conjugacy and conjugacy classes in this lecture and remark how a subgroup is normal if and only if it is conjugate only to itself. The larger a conjugacy class is, the further away from being normal it is, in some sense. We define this rigorously in a manner that is unique to this lecture series in my book, and we hint at how it relates to the size of the normalizer. The experienced listener may recognize this as a special case of the orbit stabilizer theorem of group actions, which we will see in Chapter 5. Okay, before we get started, let me implore you to watch the previous lecture if you have not already. Even if you are an expert and you know what cosets are and all about them, you likely haven't seen them in terms of Cayley graphs, and you probably haven't seen my notation of these box diagrams and how I color certain cosets blue and others red. I'll catch you up here, but it still will be helpful to see that first. Given a subgroup H of G, it is natural to ask the following question. How many left cosets of H are right cosets? Remember, the left cosets and the right cosets both partition the group, but the partitions might be different. So here's a little cartoon of what it could look like. So here are the left cosets of a subgroup H, and here are the right cosets. In this lecture, and henceforth, I will color left cosets that are also right cosets blue. Left cosets that are not right cosets will be colored red. So back to this question. How many left cosets are right cosets? Well, in the best case scenario, by some measure of best that I hope to impress upon you soon, is all of them. And in the worst case scenario, only H. Because H is always going to be a left coset and a right coset. Remember, H is the identity times H, but it's also H times the identity. In general, if neither of these scenarios hold, then it's going to be somewhat in between. There might be some cosets, some left cosets that are right cosets, but not all of them. Here's a formal definition. A subgroup H is normal in G if every left coset is a right coset. That is, if GH equals HG for all elements G in big G. We write this the same way we do with a subgroup, but we close off the right-hand side to make it a triangle. The normalizer of H, denoted NG of H, is the set of elements in G such that GH equals HG. Here it is formally. How you should think about this is the normalizer is the union of the left cosets that are also right cosets. So up here, given this subgroup H, the normalizer consists of all elements that are in blue boxes. Notice that a subgroup is normal if and only if all of the boxes are blue. In other words, if every left coset is a right coset. We've seen cases where we know a subgroup will be normal without having to check. The subgroup G is always normal in itself. The only left coset is also the only right coset, which is just G. It's E times G and G times E. It partitions the group into a single coset. The trivial subgroup is always normal because the left coset and right coset of any representative are just singleton sets. So G times H is just G times the identity, which is the same as the identity times G. We saw in the previous lecture that subgroups of index 2 are normal because there are 2 left cosets and 2 right cosets. And let me just draw the picture of that. So if this is G, and then this is H, then the other left coset is just everything not in H. So it's X times H, where X is anything not in H. But the other right coset also has the same size, so it also has to be everything not in H. So this is also HX. Subgroups of abelian groups are always normal because for any such subgroup, H, AH equals the set of all products of the form little a, little h. And we can commute these elements to write this as HA, and that is the right coset, big H times A. And similarly, subgroups that are inside of the center of a group, even if G is not abelian, are always normal for the same reason. As long as things in H commute with everything, we can run this argument through and conclude that the left coset, every left coset, is also a right coset. Let's prove a few basic properties of normalizers. First of all, the normalizer is always a subgroup. Let's prove this. Let's do the 3 steps as before. So the identity. Why does the normalizer contain the identity? Well, EH equals HE, because those are both equal to H. That's it. E normalizes H. What about inverses? So let's suppose that GH equals HG. In other words, that G normalizes H. What do we want? Let's write that down. We want to show that G inverse H equals H G inverse. Okay, how do we show that? Well, we're going to take this and let's multiply on the left by, and on the right, by G inverse. So how is that going to work? So GH, leave a little bit of space, equals HG. I'm going to write G inverse here and G inverse there. You can do anything you want if it's true. So I can multiply by G inverse on the left and by G inverse on the right. And what happens? Well, that will cancel. So this is just going to be H G inverse. And these cancel. So this is G inverse H. And that's exactly what we wanted to show. And finally, closure. Let's suppose that G1 and G2 normalize H. So G1, G2 are in the normalizer of H. Now what? Well, let's write G1, G2, H. And where do we want to end up? Well, we want to show that this is equal to H times G1, G2. And how does this work? Well, these being in the normalizer means that we can pass them through H. So in other words, we can write this as G1 times G2H. And then we can write this as G1 times, let's write H G2. And then we can regroup this and write this as G1H times G2. Running out of room, so let's move over here. And now, because G1 normalizes, I can write this as HG1 times G2. And now just by regrouping the parentheses, I have H times G1, G2. That's exactly what I wanted to show, that the product normalizes H. And this isn't too hard. Idea is that both of these things can pass right through H. So why can we pass both through? Well, because we can do them one at a time. As a corollary, every subgroup is normal in its normalizer. So now we know that this is a subgroup of G, and we know that it contains H because everything in H normalizes it. Remember, why is that? H, little h, big H, by our boring but useful coset lemma in the previous lecture. Again, why you should watch it if you haven't already. Little h, big H is H, which is H, little h. So everything in H normalizes H. So that means that H is contained in here, and it's trivially normal, I claim. So just by definition, GH equals HG for all little g in the normalizer of H. And that's what it means for H to be normal in the normalizer. Everything literally normalizes it. So that's that. Now, let's talk about how to spot the normalizer in a Cayley graph just by inspection. This is D6, and the subgroup H is generated by a reflection F. Here are the left cosets of H. Again, if you're not familiar with this or comfy, watch my previous lecture. And I will continue to denote the left cosets that are also right cosets in blue and the others in red. So with that knowledge, you can say that the normalizer is just these two cosets, or the union of those. But let's suppose that we didn't know that. So if we collapse G by the left cosets of H, and we disallow H arrows, then the normalizer consists of the cosets that are reachable from H by a unique path. So what do I mean by that? So let's do an example. This coset, how can I get there from H? Well, there's two ways. I can follow the R arrow, or I can from 1, or the R to the 5th arrow from F. That is not a unique path. There's two ways to get there. This coset, I can follow the R squared arrow from 1, or the R to the 4th arrow from F. And of course, the R to the 8th arrow is, R to the 8th is equal to R squared. So that's not a different, it's a different path. It's just the same element. In contrast, this subgroup, or this coset here, how do I get there from here? Well, I can follow the R cubed path from 1 or the R cubed path from F. That's the same element. Therefore, this coset is in the normalizer. It's worth pausing this lecture and thinking about why that is true. It's really just not much more than using the definition, and I guess it takes a little bit of thought, but not much. Here is the normalizer. It's the union of these two cosets, and we just proved that that's a group. And we can see that this group happens to be isomorphic to the Klein-4 group, V4. This generalizes in the predictable way. If n is even, then the Cayley graph, or a Cayley graph of the dihedral group Dn will look a lot like this. It has n-fold symmetry instead of 6-fold symmetry. And in particular, there'll be a blue coset over here, reachable by a unique path from H. So the normalizer of Dn, if n is even, is just the union of these two cosets. That is the subgroup generated by F and R to the n over 2. However, if n is odd, then there is no coset right here. And so the normalizer of H is just going to be H itself. Let's move on to conjugate subgroups. For a fixed element G in the group, let's call it big G, the set GHG inverse is just the set of all products of the form G times an element H times G inverse, where that element ranges over all of H. This is called the conjugate of H by G. Let's make several observations. First of all, for any element G, the conjugate of a subgroup by G is also a subgroup of G. How do we prove that? Well, it's just straightforward. The identity E can be written as something in here. It's just G times the identity element times G inverse. Remember, we're writing this, every element in here has that form. What about closure? If we have G H1 G inverse times G H2 G inverse, well, the inner G and G inverses cancel and we get G H1 H2 G inverse. And yes, that has the same form as this. H1 H2 is the element that is in H. And finally, for inverses, the inverse of an element GH G inverse is just G H inverse G inverse. You can, to check that, you could just multiply these things together. I mean, why is that? So GH G inverse times what I claim is the inverse, GH inverse G inverse. Well, those things cancel. And then the H and the H inverse cancels, and the G and the G inverse cancels. Observation 2. GH1 G inverse is equal to GH2 G inverse if and only if H1 and H2 are the same. I'm not even calling this a theorem or proposition. This is just an observation, because we can multiply on the left by G inverse and multiply on the right by G, and we get that H1 is equal to H2. Later, we'll prove that every conjugate of a subgroup H is isomorphic to H. We just don't know how to do that yet because we haven't discussed homomorphisms. If the left coset GH equals the right coset HG, then right multiplying both sides by G inverse yields the equality GHG inverse equals H. In particular, if this holds for all elements G, then so does this. This gives us a new way to check whether a subgroup H is normal in G. The following three conditions are equivalent to a subgroup H of G being normal. The first one is the definition. Every left coset of H is a right coset. The second one is the condition we mentioned above. Every conjugate of H is equal to H. In other words, there's only one conjugate subgroup. And the third one is new. It says if we take any element in the subgroup H and we conjugate it, we remain in H. In other words, H is closed under conjugation. Now, the first two of these are easily seen to be equivalent. Just take this one and multiply on the right by G inverse, and you get that. And now multiply this by G, and you get back to here. 2 implies 3 is also straightforward. If you have this equality, that by definition means conjugating any element has to remain in there. So I'm going to complete this. I said I'll leave it as an exercise. I'm going to actually do 3 implies 1. You can do 3 implies 2 if you want to as an exercise. So let's suppose 3 is true, and we want to show every left coset is a right coset. So to show that, we need to show both containments. So let's take an element. I'm going to do this. So let's take an element G H in the left coset G H, and we're going to use this condition. So then G H G inverse is equal to H1, which is in sum, or is equal to sum H1 in the subgroup H. Well, that means that G H equals H1G, which is in the right coset HG. Okay? And that's it. We took an element in the left coset, showed it's in the right coset. Now for the other containment, you can basically do the same thing and just take G inverse if you want. Instead, I'm going to actually take HG. I'm taking an arbitrary element in big HG. Now, I'm going to write G inverse HG. That's equal to some H2 in H. So again, I'm conjugating not by G, but by G inverse. And similarly, we can multiply both sides on the left by G and get HG equals GH2, which is in GH. So we took an element in the right coset and showed it's in the left coset. So that's why these are equivalent. Sometimes one of these three conditions is much easier than the others. For example, if you want to show that a particular subgroup H is not normal, you might not want to check every single left and right coset because it might take a long time to find one that's not a right coset, especially if there's infinitely many of them. Similarly, you might want to check every single conjugate subgroup. However, if you can find just one element in H and something in G that conjugates it to not be in H, then you know H cannot be normal. For another example, if G has a unique subgroup of size, let's call it M, of order M, then that must be normal. Why? Which condition is going to help? Well, for that one, look at condition 2. If there's only one subgroup of a particular order, then every conjugate of that subgroup has to be itself, right? Because there's nowhere else to go. So in other words, for this first condition, or this first example, you should use 3. And the second example, you should use 2. At this point, I want to show you a family of groups that exhibits an interesting example. And I'm going to keep up these equivalent conditions for reference. If G is infinite, then it's actually possible that there could be a subgroup H and a conjugate of it which is properly contained in H. Now, this would have to still be isomorphic to H. That's always the case. And this shouldn't be too much of a surprise because the even integers are contained in the integers, but the even integers are still isomorphic to the integers. You can't have something like this for finite groups. But such an example cannot be normal. You see why? If you don't have equality here, then you break this second condition. However, if you have such an example, then it must be the case that there's some element in G, call it G1, and some H in subgroup big H, whose conjugate, G1H, G1 inverse, is not in the subgroup. For some G1 in G and H in G. You see why that is true? Because that's condition 3. So in other words, if something nests it deeper inside, subgroup that is, then something must take it outside. Anyways, going back to this example, this is from the field of geometric group theory. There's a family of groups called the Baumslag-Solitar groups. They're defined by the following presentation. So there's one for each m and n that are positive integers. And these groups are generated by A and B, subject to BA to the m, B inverse equals A to the n. And here are two matrices that can represent those generators. And I'm only showing you this family so you have some context as to where this next group that I'm going to show you comes from. So this is the Baumslag-Solitar group 1, 2. So it's generated by A and B, and BA, B inverse equals A squared. Consider the subgroup H generated by A and conjugate that by B. So BH, B inverse
is generated by B inverse, which is equal to A squared by this relation. And that's the even powers of A. And so that's strictly contained in the odd powers of A, all powers of A, which is the subgroup itself. So H cannot be normal in G because it satisfies this condition here. There's a conjugate of it that is a proper subgroup of itself. Here are some pictures of this group from the Wikipedia page and an animation. So here's part of a Cayley graph up here. And if this is, let's call this the identity, B inverse equals A squared. So the subgroup generated by B inverse, when you do that, is you're getting this, and this, etc. You're skipping every odd power of A. Now this is not the entire Cayley graph. The Cayley graph is built with these sheets. I have trouble visualizing this as well. I haven't wrapped my head around it, but I think it's fun to look at and think about it. And these sheets are put together in a tree-like fashion, which you can see with this picture here. It's like a cross section of it. And here's another static picture of that. So if you like that, well, you got something to look up online. Start with the Wikipedia page, and then just do a Google search and go in that rabbit hole if you want. I want to finish this lecture with a really important example involving the group A4, the alternating group. We will return to this example later in this section and also in chapter 5 when we study the orbit stabilizer theorem. So here is the subgroup lattice of A4, and each subgroup I've listed by generators. These have order 3, so they're isomorphic to Z3. These are Z2, and this is the Klein 4 group. You recognize that little diamond shape. So I have circled the conjugacy classes with these dashed lines. Clearly, the entire group and the trivial group have to be normal, as does N, because it's the only subgroup of order 4. Now, the subgroups of order 3 are all conjugate. You got to be careful. It's not the case that 1, 2, 3, this permutation is conjugate to every other 3 cycle. That happens in the symmetric group, but not the alternating group. And it may not even be the case that 1, 2, 3 is conjugate to 1, 2, 4. I don't remember. But this subgroup right here consists of the identity 1, 2, 4, and the inverse of that, which is 1, 4, 2. And I claim that 1, 2, 3 is conjugate to one of these 2 permutations and not the other. So these 4 subgroups are conjugate, and then these 3 subgroups of order 2 are going to be conjugate as well. For each one of these, let's think about what the normalizer is. So N is a conjugacy class of size 1. It is normal, so its normalizer has to be the entire group. Remember, that's an if and only if thing. A subgroup is normal if its normalizer is everything, if all of the cosets are blue. Now let's look at H. What's the normalizer of H? Well, it has to contain H, but there's only 2 subgroups that do. So it's either H itself or it's A4. And, well, it's only A4 if it's normal, and we know this is not normal. Now, if you don't believe me, you can actually write down 1, 2, 3. Let's pick something else. 1, 2, 4, and 1, 2, 4 inverse. 1, 4, 2, doesn't matter which one we put where. And we can show that whatever we get is not going to be in this subgroup. So this is not normal, and the normalizer contains it. So the normalizer has to be it, because there's nothing bigger that it can be. And similarly for all of these, they are their own normalizer. And finally, what about this? So the normalizer of K is, well, K is not normal, because it's in a conjugacy class of size 3. So the normalizer either has to be K itself, or it has to be N. Cannot be A4 because it's not normal. And I claim that the normalizer of this is actually N. I'll let you check that if you want to. You can, well, just wait till the next slide. Here is that slide, and here are the particular elements. So A is the permutation 1, 2, 3, which generates the subgroup H. X is the permutation 1, 2 times 3, 4, which generates the subgroup K. And then n is generated by x and z, which is the permutation 1, 3 times 2, 4. And finally, we just mentioned that b over here is the permutation 2, 3, 4. Now, looking over here, n is normal. All three of these left cosets are right cosets. Oh, by the way, I'm continuing my coloring scheme of coloring left cosets that are right cosets with blue and the other ones with red. So here's the partition of left cosets on the Cayley graph, and here's the partition of left cosets in those so-called boxes. The normalizer is equal to the union of the blue cosets, which is G itself, and so it has index 1. Let me highlight that number 1. We'll come back to it. Now for K, there ends up being 2 left cosets of K that are equal to right cosets. That's not obvious, but you could check that. Each of these left cosets, well, this one is a right coset, but this one also is as well. And there's 4 that are not. So that means that the normalizer of K is the union of these 2 cosets. So it has index 3 in the subgroup lattice. Remember, K had index 6, and the normalizer is index 3. So in that picture from the previous slide, when we had A4, and then we had N, and then we had K, and we had, we had 2 other conjugates of K. And this is the trivial subgroup. So with something like this, the normalizer of K, we said is either itself or N. Now we know that it's N. And finally, H, the only left coset of H that's a right coset is H itself. So the normalizer is equal to H. H has index 4. That's 4 cosets. So the normalizer has index 4. So let me circle this 4. Because this index is 1, N is truly normal. Over here, H is, I say, as unnormal as it could get. It's the worst case scenario where only the coset that has to be a right coset is. I say that H is fully unnormal if only one coset is blue. And then K is this in-between case. It's not fully unnormal. There's at least one other left coset that's a right coset, but it's also not normal. Okay, now what did I say about these numbers? 1, 3, and 4. Where do those come up? Let me show you that previous slide one more time, just quickly. Okay, here it is. What are the sizes of the conjugacy classes? Well, N is in a conjugacy class of size 1. K is in a conjugacy class of size 3. And H is in a conjugacy class of size 4. Remember those numbers? The index of the normalizer of N in A4 equals 1. Well, the index of the normalizer of A4, so the index of the normalizer of K in A4 is equal to 3. And the index of the normalizer of H in A4 is 4. The size of the conjugacy class in each case. Do you think that's a coincidence? Of course it's not. Proving that will be for another day. But let's finish this lecture with a definition that captures that idea. So this definition is unique to this lecture series and my book, but I think it's really helpful, especially when we get to CELO theory. Suppose H is a subgroup of G. It could be finite or infinite, but it has finite index, so it has finitely many subgroups. Let's define a term that quantifies the proportion of cosets that are blue. So remember, the proportion of cosets that are blue is, well, if H is normal, that's just 1 or 100%. And then in the worst case, when only h is normal, that's 1 over n. So it's going to be between those two extremes. We'll call this fraction the degree of normality. So the degree of normality of h, let's start over here. It's the number of elements x in G for which xh equals hx. That's just a fancy way of saying it's the number of elements in the blue cosets divided by the total number of elements in the group. So it's the proportion of elements or of cosets that are blue. That is just 1 over the index of the normalizer of h and G. Remember, the normalizer are the blue cosets. And by Lagrange's theorem, remember by Lagrange's theorem, the size of a group is the size of a subgroup times the number of cosets of that subgroup. So by Lagrange's theorem, we can write this as the size of the normalizer divided by the size of the group. If this fraction, this degree of normality is 1, then h is normal. Every coset is blue. On the other end of the spectrum, if this degree of normality is 1 over n, remember n is the index of h and G, that just means that h is the only blue coset. The normalizer equivalently is equal to h. We say h is fully unnormal. Finally, if this proportion is between 1 over n and 1 strictly, we'll say that h is moderately unnormal. And the big idea is that the degree of normality measures how close to being normal a subgroup is. And what I teased you in the previous slide, we revisited that subgroup lattice, is that degree of normality, or at least the reciprocal of it, is the size of the conjugacy class. And that is a special case of something called the orbit stabilizer theorem. We'll see in chapter 5. But it's really important, I think, to see this before we get there. So we'll see this. We'll prove it, or at least we'll sketch a proof. There is a proof in my book, but I don't think I'll do it. I'll sketch it later. But we'll also see an analogous statement when we get to conjugacy classes of elements. There's a very similar definition and theorem saying that the size of the conjugacy class of an element is the index of some other group, which is called the centralizer. So that's coming up in a few lectures, and there's more fun in the meantime. So stay with us.